Since these two atoms of a diatomic molecule connected to each other through a weightless rigid rod are, then only rotation of molecule takes place, not vibration. By definition of center of mass, we know m1 r1 equal to m2 r2. Then we will get r1 equal to m2 r2 divided by m1. Mark this equation 2. Put this 2 in 1. We know that r equal to r1 plus r2. Then if you will put this, it will become r equal to r1 plus r2 m2 r2 plus r2. Then just take the LCM. This will become m1 r2 and this denominator is m1. So just take out the r2 common, m1 plus m2 r2, and this is m1. So r2 equal to, what was that here? Here it is r equal to m1 plus m2 upon m1 r2. So we will get r2 as m1r divided by m1 plus m2. See, r2 equal to m1r, m1 plus m2. Similarly, we will get for r1 as m2r, m1 plus m2. Just see this r2 m1, r1 m2, and this is same r upon m1 plus m2. Mark this as 4. Then the moment of inertia is I equal to I1 plus I2, and we know I equal to m1 r1 for atom A, and for atom B m2 r2 square. So just add it and just put this value here, and on place of r2 put this value here, and r1 on place of here. So I equal to m1 and this whole square plus m2 r2. If you will square it, m2 square r2 m1 plus m2 ka square, and similarly like here. Then take out the m and m2 will be common. If see here, m1 m2 square r m2 m1 square, so m1 m2 will be common. Then m1 m2 common, then here it will be m2 left, then here it will be m1 left. So m1 plus m2 and r square will be common, m1 plus m2. So in the denominator it is squaring, so just cancel it out. We will get m1 m2 divided by m1 plus m2 r square. This whole term, we know this is reduced mass, which is represented by mu. Then we know rotational kinetic energy of the system is E equal to half I omega square, and we know angular momentum L equal to I omega, that is moment of inertia into angular frequency. Then this omega will be L by I. E equal to half I omega square, then omega is L by I, then L by I ka square. Then we'll get E equal to L square upon 2I square. Then I here भी है, यहाँ पे भी है, तो we will cut it, then it will become single I. Then E equal to L square upon 2I. Now quantum mechanically we know that angular momentum is L equal to under root J plus 1 h bar. J is nothing but orbital quantum number, and I is the moment of inertia, E is the energy, rotational kinetic energy of the system. So we'll put the value here, and since it is squaring L square, so we'll square it, then we'll get J plus 1, and this is h bar square, since this is outside of the square bracket, under root bracket. So, and this is 2I. Then in general we will get Ej equal to J plus 1 h bar square. I is will put on place of I is mu r square. Now let's see the spectrum. First just take out the energies. When J equal to 0, then Ej, by putting on that formula, on this formula, we'll get E j equal to 0, then E0 equal to 0. If we will put j equal to 1, then E1 equal to 1 j plus 1 h bar square 2 mu r square, that is 2 h bar square upon 2 mu r square. If j equal to 2, then this 6 h bar square 2 mu r square. If j equal to 3, then E3 equal to j plus 1, that is 3 plus 1 h bar square 2 mu r square. And these transitions are possible only when the difference between the two levels is equal to the h mu. So we should put E1 minus E2 equal to h mu. Okay, the selection rules is possible when the delta j equal to plus minus 1, means if we will subtract any two of the levels, then we should get either plus 1 or minus 1 value. Then only such type of transitions are possible in rotational spectra. Now frequency of spectral line. Rotational spectra is always obtained